geometric description of what this arctangent of absolute T over sigma is. Also because it's a bit weird to think of the arctangent of absolute T over sigma if, say, sigma is 0. If S is somewhere on the positive imaginary axis, then this is like saying we're taking the arctangent of like infinity or something, and we don't really want to deal with like what's the arctangent of infinity. You might say it's pi over 2, but just to avoid dealing with that, it's really just the argument, the absolute value of the argument of S, and that sort of removes this difficulty with what is arctangent infinity or whatever. Okay, so what's happening here is we have our complex plane, and we are cutting out a sector from it, and we're supposing that S is somewhere over in this region here. So we're bounding, we have some bound on the absolute value of the argument of S, and that will give us a corresponding bound on this error term by just saying that this is the absolute value of the argument of S. And this error term is very useful if the absolute value of T is large, because we have this 1 over 8 absolute value of T. So this leads us to consider what happens if we restrict S to be in some vertical strip in the complex plane, and we let the absolute value of T get large. Okay, so the next thing I'll do is consider S equals sigma plus IT with A less than or equal to sigma less than or equal to B, and T greater than or equal to 1. Okay, so I'm assuming that sigma is bounded between two real numbers, A and B, and we'll assume that T is at least 1, because really we're only interested in what happens when the absolute value of T is large. If we want to get information when the T is less than or equal to -1, we can just use the fact that gamma of S bar is equal to gamma of S bar, and so that'll easily allow us to translate between complex conjugates. So we really don't lose too much information in assuming that T is at least 1 here. And on top of that, it allows us to drop the absolute value signs on T, which is kind of convenient. So let me say, first of all, let me call this 10. And I'll say by equation 9 and 10. What do we get? Let's just write this, but replace all the s's with sigma plus it. So we get log gamma of s is equal to sigma minus a half plus it. And then log s, so how do you take the logarithm of a complex number? You take the real logarithm of its absolute value plus I times its argument. So this is going to be the logarithm of the absolute value of s, which is square root of sigma squared plus t squared, plus I times the arctangent of t over sigma. That's our s minus a half log s. Then we have minus s is going to be minus sigma plus it, plus 1/2 log 2 pi. And then minus our error term omega of s. Now we've shown that omega of s is some complex number that has absolute value less than or equal to this thing here. So I'm just going to write it as this thing here times some complex number of absolute value less than or equal to 1. So I'm going to write it as some theta times 1 over 8 t arctan t over sigma, where absolute value of theta is less than or equal to 1. Okay? Just because it's something that has absolute value less than or equal to this, so I've written it as this times something of absolute value less than or equal to 1. So now, let me note that, so we can just get a couple estimates. Let's look at the logarithm of the square root of sigma squared plus t squared. This is going to be, if you just rewrite it, it turns out to be 1/2 log 1 plus sigma squared over t squared plus log t. And we can write this as log t plus O of 1 over t squared. And we can do that because we're assuming sigma is bounded. So because sigma is bounded, we can take a Taylor expansion here and just say that log 1 plus sigma squared over t squared is going to be O of 1 over t squared. So this is where we use the fact that sigma is bounded. And then also, I'll just say and, arctan sigma, or sorry, t over sigma, just by a trigonometric identity, this is pi over 2 minus the arctangent of the reciprocal. This is sigma over t. And we can write this as pi over 2 minus sigma over t plus O of 1 over t squared. And again, we're just using the fact that sigma is bounded to get this. Okay, so now we have these estimates for arctan t over sigma and log root sigma squared plus t squared, and we have this stuff up here. And I'll just say you can combine them all, and I did it on my own, and it's not too difficult. You basically just push a bunch of symbols around, so I'm not going to go through it now, and I'll let you do that on your own. But if you combine all these together, then you end up with the following. Say thus, log gamma of s is equal to sigma minus a half times log t minus pi over 2t plus 1/2 log 2 pi plus I times t times log t minus 1 plus I times sigma minus a half pi over 2 plus O of 1 over t. So we get a pretty accurate estimate for the logarithm of gamma of s, assuming that we're in this vertical strip. And so this is kind of a mouthful and it's hard to remember, so I will just say that for many applications, it suffices to just look at the main terms, and if you look at the main terms and exponentiate, you get the following. You get gamma of s is O of e to the negative pi over 2t times t to the sigma minus a half. And that's usually good for applications. Okay. And you can just convince yourself that this follows from that just by exponentiating. Okay, so that's the product representation of the gamma function and Stirling's approximation for the gamma function. So in the remaining, how much time do I have? 8 minutes. Let me go through just a couple interesting things. The first being the complement formula for the gamma function, which is something that Dr. Alati mentioned last class. It's the complement formula. This states that when s is not an integer, because we want to avoid poles, gamma of s times gamma of 1 minus s is pi over sine pi s. Okay. And the proof follows pretty easily just from our product representation for the gamma function right here. We just say, first of all, okay, so here's the proof. First, gamma of s times gamma of 1 minus s. We can rewrite gamma of 1 minus s using the functional equation as gamma of negative s plus 1. So it's going to be negative s, gamma of negative s. So this is going to be negative s, gamma of s, gamma of negative s. Right, this is just that. And then this we can write using our product representation for the gamma function as negative s times gamma of s is 1 over s, product from v equals 1 to infinity of v over v plus s, v plus 1 over v to the s. And gamma of negative s will be 1 over negative s, product from v equals 1 to infinity of v over v minus s, v plus 1 over v to the minus s. The negative s and the 1 over negative s will cancel, and we'll be left with a 1 over s. And now let's just combine these products into 1, and we get the product from v equals 1 to infinity of v over v plus s times v over v minus s is going to give us v squared over v squared minus s, minus s squared. And v plus 1 over v to the s times v plus 1 over v to the minus s is 1. So we're left with just this. And this we could also write as 1 over s product from v equals 1 to infinity of 1 minus s squared over v squared. And if you use the Hadamard product theorem that Dr. Alati spoke about on Monday, or if you took Dr. Robinson's complex analysis class last semester, I think we derived the product representation for the sine function. So you can recognize that this is basically just the sine function, and this turns out to be 1 over, well, it's 1 over that. It's 1 over sine pi s over pi. And of course, this is just, or yeah, it's 1 over the reciprocal of that. So this is pi over sine pi s. Okay? So it follows pretty easily just from our product representation for the gamma function. Okay, so in the last 5 minutes, I have some fun facts about the gamma function to share. So these will be fun facts. The first fun fact, I have 2 of them. We saw already that gamma prime of 1 is equal to negative Euler's gamma, which I think is kind of cool. You can also take the second derivative of gamma at 1, and you get gamma squared plus zeta of 2. Or if you like, this is gamma squared plus pi squared over 6. And I also computed gamma triple prime of 1, and it turns out to be negative gamma cubed minus 3 zeta of 2 minus 2 zeta of 3. And so you can see you're getting like values of the zeta function at positive integers coming from differentiating the gamma function and evaluating it at 1. And this sort of makes sense because there's sort of a heuristic reason why you might consider Euler's gamma to be like a pseudo value for zeta of 1. We know that zeta of 1, I mean, zeta has a pole at 1, so that doesn't really make sense. But there are sort of heuristic reasons why you might consider Euler's gamma to be like a somewhat value of zeta of 1. And so this sort of fits in nicely with that because you can think of this as like zeta of 1, zeta of 2, zeta of 3. Okay, so the second fun fact that I have is really just a fun fact. I don't think it's serious or anything. But the volume of a unit ball in Euclidean in-space, so in Rn, is pi to the n over 2 divided by gamma of n over 2 plus 1. So one reason this is interesting is because the denominator here grows like a factorial and the numerator grows like an exponential. So this actually goes to 0 as n goes to infinity. And you can also show that this expression attains its maximum value of pi, or 8/15 pi squared when n equals 5. So if anyone ever asks you what is so special about the number 5, you can say it is the dimension of Euclidean in-space in which the volume of a unit ball attains its largest numerical value. Yeah. So, yeah, that's all I had to say about the gamma function.
Really beautiful lecture, and not only was it so nicely organized, I like how I know that some of my other students have tried it and said no, they couldn't do it. So
Yeah.
you have actually obviously mastered it. And also I like the fact that he never used notes. So that's really good, unless you understand the material very well, you don't use notes. In my younger days, I used to lecture without notes, but now my memory is failing. I rely on notes. Really good. Thank you. Thank you for wonderful lecture.